False start?
No.
Now it works, yeah. Okay, hello everyone. I'm really sorry that you have to stand there. Yeah, whatever. There's one extra seat here if you want. And by the way, in case you kind of came here by accident, this is the fourth presentation on this track, on the main stage. But the first one, which is not about artificial intelligence. But fear not, the next one is also about AI. So that's just going to be one exception today. All right, so this talk will be about failures and about resiliency, because it turns out that no matter what we do and no matter how we design the systems, we keep thinking about the happy path. There are tests for a happy path, we have scenarios for a happy path, and we often forget that there is something like failures. We often forget that some things might break. And what I want to do today is just give you a very, very quick tour over different patterns, different ways, different approaches how to deal with errors. So there will be no successes today, only failures and only ways how to tackle them. So does this even work? Yeah, it does. So I came to this really nice quote that I'm not going to read it out loud because you can probably do it yourself. So that's actually true. I mean, no matter how many times I was looking at systems, especially distributed systems, it turns out that they fall apart even if the slightest part doesn't work, like the slightest service or one of the components which are not really that essential. So we want to be agile, but this is going to be a dad joke because we're actually fragile. We are building really, really fragile systems which break really, really quickly. You know this term 1 in a million. There's this terrible Polish song in the same title. So it turns out that a 1 in a million situation happens every 15 minutes if you're serving 1,000 requests per second, which is not really that much. And even if it's 1 in a billion, it will still happen once in a week or so. So you really have to be aware of that. It's not something that unusual. Now, there's another term called P99, and we are really extremely focused about P99. Like, my response is within P99. The P99 is great. But it turns out that if you open Facebook, it actually loads 350, it makes 350 requests just to open the main website. Like, most of these are just ads. But anyway, you essentially have 100% guarantee that at least a few of these requests will exceed P99, which essentially means like all your statistics are not that important. And the same actually applies to P99.9 as well. So moving quickly to the actual patterns, and by the way, I'm not going to give you some code samples. I'm not going to be giving you like concrete examples of how to deal with stuff. I will just be showing you a catalog of things that you can look up later. And to be frank, every single slide on this presentation could be a presentation on its own. So the research is up to you. I'm just giving you a few clues. So the first pattern, the king of all the patterns, is just a try-catch. So if you don't do a try-catch in your code, the errors will eventually pop up, but in places you have never imagined. So let's take this really contrived example. So let's say I'm repaying a loan, and repaying a loan consists of several nested steps. And the very last step, I'm not going to be reading this code through, but the very last step is just sending an email to a customer like, hey, your loan was repaid. And it turns out that if there's a socket exception or whatever connecting to a SMTP server, something really, really, really trivial, like, guess what? The whole process just fails because you forgot to have a try-catch somewhere in your code base. Now, I got a feedback after giving this presentation once already, or just once so far. I got a feedback that, yeah, who the hell writes code this way? Like, I mean, this is not taken out of thin air. I actually saw systems where very, very trivial task was breaking the entire business process that was running for several days because, well, running out of space is not really that trivial, but way more trivial things. So try-catch is the king, and it's the first pattern that will avoid a lot of issues. Okay, but let's move on. This comes from the title of the talk, so fallback. Now, this sounds really trivial, and in many cases it's not really that trivial to implement, but the basic idea is that if you have a try-catch, which is a great first step, you should have something in catch. Not rethrowing the exception, obviously, not just logging the exception, but still a better idea, but anyways. But maybe as in maybe you can do something useful. In some cases, it's fairly simple, and on many presentations it's really simple, as in, if that system doesn't work, just present hard-coded data, or present some fallback data, or whatever. But even in the most like non-trivial situations, like for example, I don't know, you're charging customers' credit card, and you got a rejection from the bank. Now, typically you would just fail the whole transaction, but, and I'm really stretching really far here, but bear with me. I'm just gonna spread my arms once again because it looks nice on the camera. So, because I look like a preacher. Again, thank you. The cameraman is happy about it. But anyways, so let's say you're charging a credit card and the credit card is rejected. If the customer had a really good history in the past, maybe you can just squint your eyes a little bit, allow the transaction, and have some fallback mechanism, as in contact the customer or maybe charge using a different mechanism. Or maybe that money is lost. Okay, but it's better to have a few percent of, or a few per miles of transactions failing and the money is lost, rather than failing, I don't know, 50% of the transactions because your code is broken and you cannot serve all the other customers. This is a big stretch, but just think about it. Right, moving on, retries, and I just noticed this guy has a RTFM t-shirt on its text on its t-shirt, which is really cool. Retries, another really trivial stuff. If you fail, you will not, you cannot really imagine how many times a failure can be avoided if you just retry. Why? Because there was some intermittent problem with the network. You happened to hit a node that was just being restarted, or you had a very aggressive timeouts. Timeouts will be in a second. You had very aggressive timeouts and you just hit an instance which was garbage collecting at the moment, and so on and so forth. Just try again. In many cases, it just works and no one will ever notice. And actually, if you don't do it, someone else will do it. In the worst case scenario, it's your user keep hitting F5 in the browser, which is essentially just a human way of doing retries, but much more expensive and having a much worse developer experience. Talking about retries, I don't know if you've heard about this this header called retry after. If your HTTP request fails, you can actually make a suggestion to the client after how much time he or she is supposed to retry. Right? It's basically just retry after 10 seconds or something like that. If your system is self-aware to that point where the system can actually give such an answer. Another term which is really important when it comes to retries is exponential back-off. Again, this is a topic for a brand new presentation, but basically the idea is that if you're retrying, just don't do a retry like over and over and over again, because you will DDoS another service or another API that you're calling. Make retries with some delay. And the good rule of thumb is that you're supposed to make first retries very quickly, because maybe the problem is intermittent and then you will very quickly get a successful response. However, if there is something really bad happening, once again, someone's making a photo, so I'm making my preacher posture, okay? Just pretend I'm doing the actual talk. So the idea is that if the failure is not intermittent, if it doesn't just fix itself after a few milliseconds, just keep retrying with longer periods of time. And just heuristically, it turns out that it's a good idea to do it exponentially. So after 1 millisecond, 2, 4, 8, and so on. And there's another interesting term, which is jitter. Jitter is essentially this meta-heuristic that you should not make retries with a fixed periods of time, but instead you should add a little bit of randomness. Otherwise, your retries will have a tendency to self-synchronize themselves. So many systems will do retries at the same time, causing a phenomenon called thundering hertz. I have it on one of the slides, so we'll get there. Another pretty obvious thing, timeouts. If you're calling anything that is different than just your local function, remember about timeouts. So I was running on a train a couple of years ago, and it has famously bad internet connection. There is this big number in the ping output. It's not that easy to decipher it, but it's 12 minutes. Just think about it. My network packet went to google.com and then waited somewhere for 12 minutes to actually get back. So imagine how your application, let's say you're building a desktop application or a local application or whatever, imagine your application getting a response after 12 minutes, a successful response, which is even worse. Imagine how many inconsistencies you can get in the meantime. So remember about timeouts, and always when you're calling some API or using a library, think about the timeout configuration. Many libraries have it by default. Many libraries have a timeout of +infinity, something to keep in mind. Bulk heading will slowly and gradually moving to more and more complex patterns. So bulk heading is the idea, starting from the ship metaphor, or actually where it came from. So bulk heading is the idea of putting kind of a vertical walls within the hull of the boat, so that if there's a hole in the boat, the water is only aggregated, or no, the water only appears in one of the compartments and all the others are safe. And this essentially prevents the whole boat from sinking. Now, one of them, do you recognize the ship? Yeah. This is Titanic, and they also had bulkheads. So, what the hell, you might think. Their bulkheads had doors. You get the idea. You have a wall that is supposed to isolate water from coming from one compartment to the other, but these walls had doors, and the doors were like 3 meters tall because it was more convenient for the passengers, because otherwise they would have to go up and down all the time. And the Titanic metaphor is actually pretty good. For example, in Java, when you have a thread pool, I think the default policy when the thread pool is full and the queue is full is to run the task within the in the context of the caller, which essentially means that you're thinking that you're running some code in the background. And by the way, thread pool is a great way to implement bulk heading within your application, because when one thread pool is saturated, all the other thread pools can still operate. But if you use this default policy, the job that was supposed to run in the background suddenly runs in the foreground. So your water overflows to a different compartment, essentially causing cascading failure within all the other thread pools. Another hydro metaphor is of throttling. So this is fairly simple, but again, it has a lot of nuances. So throttling is essentially making sure that your system can stop incoming requests if it thinks that it has just too much. So every system has limits, and every system has a limited capacity. It's just nicer and it's just better if the capacity is controlled by you, not by the operating system, not by Kubernetes or whatever. You are the best person, or you are the best place to figure out like how many requests you can serve. And this applies to the other side as well. So if you're calling some API, you should expect that API to have some throttling in place. I know multiple stories, which I don't want to disclose actually, where we brought down another system, a big system, just because they didn't have throttling in place. So you don't want to be in that situation. A circuit breaker is yet another pattern that I want to very, very briefly cover. So circuit breaker, putting aside the electrical metaphor here, circuit breaker is a piece of machinery, a piece of library that you can just plug into your code, which essentially cuts off dependencies which are malfunctioning. So imagine you're calling some API, and that API keeps failing and failing and failing and failing. If you keep retrying, then first of all, you will not get result anyway, because it just keeps failing. But secondly, you are overflowing that other service with your requests. Maybe it's failing because it's just overloaded. Maybe it's a better idea to just give it some space, give it some time to recover. And this is the idea of a circuit breaker. If it discovers that the error rate is too high, it just shuts off the dependency, so you get a fail-fast mechanism. So it fails immediately rather than keeps receiving the requests. There are several things to consider when implementing a circuit breaker, because there's actually much more than meets the eye. First of all, you have to think about the condition, the error condition that actually triggers the circuit breaker. It's fairly common that people just react to every single error coming from the service and treating it as a failure of that service. No, if the service returns 404, it's your fault. It's not them. All right, so you have to keep that in mind. This is not a situation that should trigger the circuit breaker to open. Another really common situation is that the circuit breaker opens and it never closes back. So this is actually a very useful feature of a circuit breaker, as opposed to a circuit breaker that you have in your wall. Circuit breakers in our systems can close themselves. So once in a while, they are just poking that failing service, and if it began working, if it began serving the requests properly, the circuit breaker closes itself and we are back to business. there were numerous outages in multiple companies where the circuit breaker just opened and never closed back. So essentially you have a malfunction that requires a restart. And also granularity. So imagine you are calling a service with 10 instances, and one of the instances is permanently down or permanently serves failures. All the other services are up. Okay? So your failure rate is in the range, what is it? A question to the audience. 10%, right? So we have a 10% error rate. Should you open the circuit breaker in that situation or not? Well, the question is, it depends, right? Because technically, you could just have a circuit breaker per each and every instance, right? I'm not saying this is a good practice, but just something to think about it. Because if you have one global circuit breaker, you will cut yourself from the 9 instances that are still working rather than just cutting off from the one that's malfunctioning. All right, so the thundering herd issue, or the thundering herd problem. So this one happens if you have multiple processes, services, threads, whatever, waking up at the same time just to realize that it's not yet their turn. So imagine you have, I don't know, some sort of a global lock and some resource, and when an event appears, you have kind of a broadcast situation. I'm coming up with this as I speak, so I hope that the example will be good. So imagine there's a kind of a message that was broadcasted to 1,000 nodes, and only one node can handle that message. So what happens is that all 1,000 nodes wake up, just for one node to pick up a lock, and when it picks up that lock, it processes that message, and all the other 999 processes or services just realize that they don't have a lock, so they go back to sleep. You have a ton of wasted resources and a lot of potential for failures. So don't implement things this way. Of course, in this example, broadcast wasn't a good idea in this particular design. Another similar problem that you might come across is called cache stampede. I don't know what's the right pronunciation, but essentially the idea is that when you have a cold cache, and the cold cache is a situation where your cache is empty, so you're asking cache and it doesn't have a value yet. So the typical implementation, I don't want to put a pseudocode here, but the typical implementation is you reach to the cache, there is no value, so the cache is empty. You compute the value, so you go to the database, you go to external service, whatever, you put that value in the cache, and you return it, right? It's as easy as that. The problem arises when there are thousands or maybe hundreds of thousands of requests hitting your service, all asking for the exact same key. Because in the most naive implementation, you will have 100,000 requests, for 1,000 whatever, 1,000 requests asking for the same key and computing the value of that key because the cache is empty. There are strategies to fix that, and you can probably come up with them yourself. For example, locking the key or returning a failure if the cache is empty and not yet populated. But it's something to keep in mind. It actually brought down, what was it, Facebook? Yeah, a few years ago. Right, moving on and moving to asynchronous systems. Asynchronous systems, we were talking previously about RPC, so remote procedure calls, or REST, or GraphQL, or whatever you want to call it. In the asynchronous systems, it's actually fairly simple because typically you don't see errors, right? You just send a message and you forget about it. So that's fine, and it's actually okay because you cannot fail on an exception if you never see it, but it brings a whole lot of new issues that you need to think about. So the simplest way of running asynchronous processing is just to have thread pools, coroutines, goroutines, actors, agents, enclosure, whatever. And this is actually a very useful design. So if you can put something to run asynchronously, just do it. If you don't have to wait for the response. Of course, once again, it brings a whole lot of problems. For example, what happens if your instance dies? What happens with the background job? Will it be retried? Was it persistent? And so on and so forth. So this brings us to message queues. So it's essentially like a thread pool on steroids, because in this case you are offloading some sort of a job to a message queue, but that message queue is supposed to be persistent. So if the consumer dies, it should retry. And once again, you have to be aware of multiple things that can happen with the consumption of the messages. And this is just a tip of the iceberg of what can fail. So for example, what if your consumer fails to process a message? Is that message lost? Is it retried? Is it retried on the same node or on a different node? Does it land on DLQ? Do you even have DLQ? Are you aware that you have a DLQ? Do you do something with a DLQ? The DLQ stands for dead letter queue, so it's a place where broken messages come. I don't want to be in your situation where you wake up one day and you have a DLQ with millions of messages just because like someone suddenly noticed that the process didn't finish. There's also this phenomena called head of line blocking. This is especially important in brokers which keep a kind of a strict order, for example, Kafka. Kafka is probably not a message broker, but whatever. So the head of line blocking is a phenomena when a first message, or one of the messages, the tip of the messages in the queue, is being processed for so long that all the other messages that are behind basically have to wait. So if you have one broken message, all the other messages that are behind are enqueued. And in the worst case scenario, you have a whole queue blocked because there's one tiny message that keeps being retried. And it gets even worse if you implemented retries the way I suggested to you, so with exponential backoff, because that means that you used to process hundreds of messages per second, but suddenly you are stuck on a single message and you retry that message with delay. So you will very, very quickly get a backlog of messages, like thousands of them. What else? Another situation that might happen, I forgot to put it here, is when you're processing a message and it takes you too long to process that message. How will the broker react? Will it just wait indefinitely? Will it assume that the message was broken or the receiver is broken? You have to be aware of these situations, and in the perfect scenario, you should know how to handle such failures. So yeah, let's talk about the uneasy stuff. So some people claim that exactly once is possible. It is not. You essentially have two ways of processing your messages. You have at least once and at most once. I'm not going to be covering like what are the pros and cons. Most of the time you want at least once so that you have retries for free. So essentially if your receiver is broken, you're just going to get the message on a different node. Just make sure your message broker works this way. Doesn't just drop the message on the floor or gets stuck. However, and this applies equally to message brokers and to RPCs or any other form of retry, you have to make sure if you're retrying something, you just have to make sure it's idempotent. It's one of the favorite interview questions, like what does idempotency mean, or which HTTP methods are idempotent, whatever. I suppose you know already that. If you don't, you have another further reading to do, but that's okay. I'm just like giving you hints what is important. One thing that is not really that popular, there's a standard HTTP header called idempotency key, which is used to deduplicate retries. So basically the idea is that if you're making a retry HTTP request which is a retry, you use the same idempotency key. And by having the same idempotency key, the server may realize that this is actually a retry and it doesn't have to perform the action twice. Idempotency key can be anything, like a transaction ID, like an action ID, whatever. Something that you can use to distinguish retries from each other. Outbox pattern, just leaving it here as a hint, that deserves a whole other presentation to hold. But essentially the idea of the outbox pattern is that if you have two resources, a local database and you want to notify someone using a message queue, this is a very good bulletproof pattern of doing it in a single transaction. So sending a message or pushing a message in the at least once manner and storing something in the database happens kind of as a guarantee within the same transaction. Requires some work, but it works. All right, part 3, distributed systems. So moving on in the ladder, or in the iceberg of more and more complex topics. So there's leader election, something that you probably did at least once or twice in your life, using whatever mechanism you want. So it can be a Redis lock, it can be a database lock, it can be a lock in Kubernetes resource, whatever. That's not the point. You choose a leader in order to have a single node, ideally a single node, and ideally at most one, not at least one, ideally have a single node that is kind of distinguished from all the others. Now, the mistake I saw many times is that the leader is actually the only worker, so the only place where the work happens. So you have a bunch of nodes, and there's one leader, and it's the leader that runs the reports, or it's the leader that makes a dump of the data and something. Now, this kind of works, but what you actually want to do is to have a leader that's more like a coordinator. So it's the leader's responsibility to distribute the work among other nodes rather than doing all the works by himself. Why? Because first of all, if the leader dies, you will have to repeat the work on a different node, and also if the leader dies, you have to elect a new leader, which always brings some latency and some inconsistency, or it might lead to some inconsistency within the process. Now here we are entering kind of an exotic territory, but still I want to show it to you just to give you an example of like how different systems can work. So this is exotic because it doesn't work well in the cloud environment. But in case you're not working with the cloud, maybe it's going to be useful to you. So imagine that rather than having one centralized database, and maybe that database is behind the browser and behind an HTTP call from the browser to the server. But imagine you just have a local database somewhere on your node, on your desktop, whatever. Imagine you are storing the data right there in your local database, and then just replicating it as if it was a master-slave, or sorry, primary and secondary type of scenario. Imagine you are just replicating stuff to that kind of centralized database. What is the point? Well, the point is that if your centralized database is down, you still operate. It still works. Of course, it brings a whole lot of issues with consistency, with conflicts, and so on and so forth. But just think about it. What happens if your system can actually store data locally, as opposed to always reaching to some remote database that obviously can be malfunctioning? So this brings us even to the very, very broad topic of the offline-first applications. So this actually distinguishes the good, for example, mobile apps from the bad ones. The good mobile applications work offline, basically. If you open an application when you are in the train with 12-minute ping, and it just works, maybe it's degraded in some sense, but still it just works, that's awesome. But all too many times you open an application and you have a slightly worse internet connection, everything just breaks, and you get some random error. I had this application that shows a ticket to Metro in Warsaw, and it actually threw me an exception. It was bin creation exception. So I think I know what they're using as a backend, but this was the pop-up, right? This was a tip at the bottom of the screen, like bin creation exception, cyclic dependency something. It wasn't like internet related, but anyways. So offline first, and if you don't want to be offline first, you also can have a term, I don't know if I came up with it myself or I just Googled it somewhere. A failure backlog is essentially a pattern where if there's an exception when you are storing data remotely, put it in kind of a local backlog or kind of a local write-ahead log or whatever you want to call it, and wait until the internet actually comes back. And then you will just drain that backlog and all the data will be synced. Once again, if you use a good mobile app, sometimes it just says with a small tooltip, like, we are offline, I will synchronize as soon as possible. That's great. It's pretty seamless, right? Work this way rather than assuming that the internet is always there and the database that's somewhere over there is always there. Liveness versus readiness. Like, raise your hands, who implements these two endpoints like exactly the same way? Like, liveness calls readiness or vice versa? Honestly. Or maybe you don't know what it is. So essentially in Kubernetes, there was just one hand, so I have to now get out of this somehow. So in Kubernetes, you have two kind of so-called probes. One says that the application is alive, essentially it waked up. And the second one says that the application not only is alive, but also can serve requests. What is the difference? For example, you can take that time between being live and being ready and warm up some caches, or maybe exercise some hot paths so that the code is being compiled or whatever, and in which case the orchestrator, like Kubernetes, will know that this service not only is alive and kicking, but it is also fully capable of handling 100% of the traffic. So it's a subtlety, but it's worth thinking what should you put in one versus the other. And part 4, architecture. So a dry run. A dry run is a fantastic pattern. If you're doing a little bit of DevOps, you probably know Terraform Plan. Terraform Plan, as opposed to Terraform Apply, is essentially telling you what it is supposed to do versus just doing it, right? So the Terraform Plan will tell you that if you run me in not a dry mode, because Terraform plan is the dry mode, if you run me not in a dry mode, I will create these resources, delete these resources, rename, yada, yada, yada. You have time to think whether this operation is actually what you want. In the context of our systems, and this is actually fairly complex to implement, but it's worth in some critical cases, if you have a very complex business process, it's worth to implement such a pattern so that if you're troubleshooting or if you are not sure what's going to happen, you just give user an ability to look ahead what will happen within the system. I'm going to send that email. I'm going to make that network call. I'm going to delete these records, so on and so forth. This is even useful for end users. Like imagine you are just a normal person clicking a button and not being afraid that you're going to do something really, really bad, because upon clicking a button which says dry run or test, it will just give you a listing of the things that it's gonna do. How to implement it, that's a whole different story, but once again, I'm just giving you a hint. If you don't have a dry run and if you already screwed up, it's good to have a planned so-called compensating transaction. Essentially, the idea is that if you did something bad, you should have a plan, you should have a function, you should have a procedure how to roll it back. And by rollback, I mean even the things that are really complex. For example, you send a text message or an email to a customer and you realized after the fact that it was broken, so you did something incorrectly. The compensating transaction will actually have an email template with an apologies to that client, right? We sent that previous email by mistake, sorry for that. This can be automated if you plan in advance that you can make such a mistake. And having a compensating transaction actually brings us to the Saga pattern, which once again can be probably a whole conference, vaConf, a hint for you, which is basically the implementation of the long-running process in which every step kind of commits to the database or performs side effects. But if it breaks in the middle, you have a whole queue, or actually a whole stack of compensating transactions which roll you back to the consistent state. So that's another thing. Throttling side effects. So that's a very quick story. I once sent 700,000 text messages to a single person. Right? We can talk later how it happened. But if your system is capable, for example, of sending text messages, it's worth having a mechanism making sure that you're not sending more than, 5 per second or something like that, because probably that's a useful limit to have. It's also worth having a so-called kill switch. So a kill switch is kind of a background mechanism in your application which figures out that your application actually went crazy, right? It happens with the company called Knight Capital. You probably know the story, but for those of you who don't, it was a company who had a bug in their software trading on the stock exchange. They were losing it was $1 million per second. That is how fast the system went hairy. If they had a kill switch, so basically a simple mechanism running in the background and seeing that, hey, you're probably losing too much money at the moment, better to just shut down because it seems like you have a bug, that would be a whole different story. As a comparison, within 1 second, Bill Gates makes just $8,000 rather than 1 million. Graceful degradation is another pattern that you should consider. So if you have especially if you have a distributed system, which consists of 100, maybe 1,000 different microservices, first of all, God bless you. And secondly, do you really need all 1,000 services to fulfill your business process? Well, they are there for a reason, right? So you need them in the end. But how many of these services are actually essential? Like as essential as the system barely works, but it still works. You can still do the minimal work, right? How many services you can right now kill on production or add a proxy that increases the latencies by 100% or 100 times, sorry. How many services are actually absolutely essential, so-called tier 1 services? Think about it, like how many services you can kill now on your production and customers won't notice, or it would just be a minor inconvenience, right? And I think that's the last thing. So testing resiliency, that's a big thing. So by testing resiliency, I mean utilizing stuff like chaos engineering, Chaos Monkey, Chaos Gorilla, Chaos whatever from Netflix. probably you know what it is, but basically it's just injecting faults into your system and making sure it still somewhat behaves. So testing how it runs with some services down. Coming back to the example we had just a second before, like what happens if you kill a bunch of less important services? Will it impact the ordinary work of the system? Oh, I have a piece of code actually. This is ToxiProxy, which is yet another tool that you can use essentially in your integration tests to see how it behaves in this particular example, how it behaves if MySQL has some unplanned latency. Will it fail? Will it fail gracefully, or will it just break entirely? And the last part, I have 40 seconds. This is just enough. So observability, this is a no-brainer, have it, right? Period. Just make sure you don't have too much. Yeah, I said it. There's this term death by 1,000 dashboards. There's also a death by having millions of dollars in the APM costs. And I'm looking at you, it's recorded. So every APM is expensive, sometimes even more expensive than the actual cloud costs. And the last 9 seconds, the culture or the engineering culture. Have postmortems, have premortems. So premortem is like figuring out why the system failed and how could we prevent it even before it actually failed. So very useful process. A few links so that you know, so that you have some way of moving on. And yeah, thank you so much. This is the link to the slides. I don't have much time, but I don't have any time left, but feel free to ask questions.
Yeah, we have definitely time for some questions.
Oh, okay, awesome.
Can you pass the mic?
Hi, hello. So I have a question for you. Could you recommend a way to synchronize circuit breakers within service, within system, or maybe set of systems?
Oh, that's a tough question. So, but basically, circuit breaker is a pattern. I think you all had the question. Circuit breaker is a pattern that works, or most of the implementations work locally, meaning that every node has its own circuit breaker history and has its own circuit breaker statistics. I am aware of the problem, and I never saw the right implementation because theoretically you could share circuit breaker state using some global database or Redis or whatever, but in my opinion, it adds way too much complexity to the error handling code. So I would rather have circuit breaker working alone on every single node, so that I let every single node to discover on its own that something is broken, rather than having this fairly complex and convoluted like system within a system of circuit breakers synchronizing with each other. I didn't saw an implementation that works like properly this way. So I hope this answered your question, even though the answer is better not.
Yeah, thank you. I know there is some implementation connected with mesh networks, with that mesh provider gives something like that for you, but I haven't tried it yet. I know there is an option like that, but this is not within your code, but this is something like outside.
So you're talking about service mesh, right?
No. In particular, we have synchronized circuit breaker in our system, but I know there is a way to actually do it in the service mesh.
Kind of a seamless way. Yeah, so something I didn't cover, service mesh will implement some of the patterns that we covered here, like retries or maybe circuit breakers, timeouts, and so on and so forth. It seems like we still have some time.
Yeah, one question maybe, if there's one. No, apparently not.
Oh, that's a shame. Thank you very much then. Thank you.